Any integration project developed using the tools provided by integration vendors follows widely recognized integration patterns. It's because these patterns were recognized after years of experience, and the drag and drop doodlewares are built on top of these patterns. A message is a data structure that holds some information, for example, a mule message. In this video, we'll try to understand different types of messaging patterns. As usual, I've placed the video timestamps in the description below. So let's get started. Based on the processing types, I have segregated the messaging patterns into synchronous and asynchronous. So before starting with messaging pattern, let's try to understand the processing types. So basically, at a high level, we have synchronous and asynchronous processing. Synchronous processing again has sequential and parallel processing, whereas asynchronous processing usually means non-blocking processing. So let's understand all of these processing types. Let's first start with a sequential processing. We have a thread T1 which starts a task T1. Then the output of task 1 is fed to perform the task 2, which means that task 2 depends on task 1, and the output of task 2 is provided to task 3, which again means task 3 is dependent on the output of 2 and 1. Now this looks good. It's sequential, one after the other. But what if we have a scenario where we have a task 4 and the task 4 is dependent on the combined output of task 2 and task 3, and task 2 and task 3 both are independent of each other. It's just that task 2 needs the output of task 1 and task 3 also needs the output of task 1. So effectively, task 2 and task 3 would be independent of each other. So what we can do, if we go with a sequential processing, we might have an inefficient program, right? We want to improve its efficiency. So what we can do, we can make these two tasks parallel and combine the output and give it to task 4. So let's see that in next slide. So this is parallel processing. We have a thread T1 which starts a task 1, and then we have 3 independent tasks, 1A, 1B and 1C, which are spawned by 3 new threads. And finally, the output of all these 3 tasks is combined together and then given to thread T1, which again runs the task 2. So in plain Java terms, it's just we are joining all the 3 threads. So this looks good. We are getting some improved performance when calling 3 independent tasks. But again, there is a problem over here. The problem is that this particular portion is blocking the thread T1. There could be a scenario where task 2 doesn't need the output of task 1A, 1B and 1C together. Maybe there is a task 6 or 7 which would need the output, right? And task 2 would need it immediately. So what we are doing is we are blocking the thread T1 unnecessarily, whereas the thread T1 could have done something useful while the thread T2, T3 and T4 were fetching the data. So that's the problem. And the solution to this problem is we need to make the program in such a way that it doesn't blocks the thread T1. So it should be non-blocking, right? And that is what we do in asynchronous processing, which is also called as non-blocking processing. So let's see that in action. We have thread T1 which is starting a task 1. Then we have 2 different threads. T1 is already present. We have a thread T2 which will do a task which is called as 1A, and task 2 doesn't require the output of 1A, so thread T1 is not blocked. It just starts with the another task. So what happens is when T2 executes the task 1A, what it will do, it will return the task something called as promise or a future. The term promise comes from JavaScript and the term future comes from Java. So in Java we have something called as futures. Future, as the name suggests, it will give some value in the future, not immediately. So an object is populated with no values effectively, right? So another thread will do this task, and T1 is not being blocked. It continues to do its job because all the other tasks are independent of 1A. So once the task 1A is finished by the thread T2, the thread T2 will populate this promise. We have the T2 result, right? So its job is to populate the future or promise object. So now when the T1 thread runs the task T3, which needs the output of task 1A and task 2, right? So what it will do, it will invoke the future and get the data from there. So it's T1, and T1 is running this task T3, and it has the final output is task 3 plus the promise data that we have. So in this way we have not blocked the thread T1. The thread T1 is flowing without any obstruction, and the intermediate data that was required was given by the promise. Now this looks good, and this is how non-blocking processing works. But this was a very short idea. Again, there were some refinement done to this mechanism, and that was when reactive programming came into picture. So the Mule 4 runtime is based on the reactive engine, right? And this is what happens when it does non-blocking operations. So it's asynchronous processing. So that is what is the difference. Even if it is parallel, that doesn't mean it is asynchronous. If it is asynchronous, it has to be non-blocking, because in the previous slide we saw that even though it was parallel, it was blocking the parent thread. So that's the difference between synchronous processing and asynchronous processing. So again, if you try to implement this in Mule flows, it's not possible that you will be able to achieve this functionality as it is by doing a drag and drop, because to achieve asynchronous you have something called as async scope, but async scope is as good as fire and forget, right? So you have to implement some mechanism that would help you to collect the value, like it happens in this case. It's getting the promise data from the promise object. So maybe you can add some queues in async scope and push the message, and then the other system pushes the message to other queue and then consume the message. So we have to do that manually in a Mule flow as far as this type of flow implementation is considered. So now that we have understood the synchronous and asynchronous messaging pattern, let's start with the synchronous messaging pattern. Let's start with request reply messaging pattern. So this is the simplest type of synchronous messaging in the request response pattern. Here the source makes a request to the target system, and the target system in turn processes or acknowledges the request and returns the response to the source system. This pattern is generally used between APIs and system which require information from other system before they can continue with their task. And on the similar lines, we have a request reply pattern with a retry. We use this pattern when the target system and source system's connections are unreliable. So in that case, it could happen that the connection might be weak or the target system goes down. So in such cases, we add a retry mechanism. Like if we observe, here we have demonstrated a timeout. In case of timeout, it retries, again timeout, it retries, and there is a certain limit on the number of retries, and after that it should stop. So there are multiple ways in Mule to do this. You can either establish a reconnection strategy, like you can configure, if it is an HTTP requester, you can configure a reconnection strategy and give the amount of retries and the backoff time. And we also have other option, which is until successful. Well, there is a subtle difference between the reconnection and the until successful. So when to use a reconnection strategy. Use a reconnection strategy when your connection is really unreliable, when you believe that the error is occurring at the connection. Maybe the connection gets timed out, or maybe the server is down. In that case, it makes sense to use a reconnection strategy. On the other hand, you should use an until successful in situations where you believe that there is a particular error message that occurs frequently, and maybe after certain retries that error message might go away. So in until successful, you define the condition for failure and you try until the failure gets eliminated, right? So that is the difference between until successful and reconnection strategy. The next one is the polling messaging pattern. Take an example of an online food delivery application. Whenever you place an order for a food item, there is a certain workflow which usually finishes off within 30 minutes or 45 minutes. So it's like the order is taken, the restaurant prepares the order, and it's dispatched and it gets delivered. So there are four different stages that happens in the order, right? So in such cases, once the order is placed, your application, which is the source over here, continuously polls the target. The target is the online delivery site. They might have exposed some APIs, so it continuously polls the target system to get the details of the order, so that the order is placed, the order is confirmed, and then the restaurant has prepared the order, and then it gets dispatched. To get all these details, the source system, that is your mobile application, continuously calls the target system, which means that it continuously polls at certain intervals of time so that it knows where the order is. So that is the polling mechanism. So unless and until it gets the data, it keeps on polling, and once it gets the data, the processing is complete. So now the question arises, when to use this messaging pattern. Use this pattern when you're aware of the frequency at which the data changes at the target system, so that chances of getting a response from the target system with new data is high, and that would lead to better utilization of resources. In Mule, there are few connectors which help us implement this pattern. For example, we have the on table row, which helps us in getting data whenever there is a new row in the table. So we can set a polling frequency using the cron expression, or we can set a fixed frequency. So in this way, we can implement a polling mechanism on a database table based on the new row. We also have a scheduler which can start a flow using a cron expression or a fixed frequency mechanism. So now, what could be the drawback of this type of messaging pattern? One of the drawback is it could get heavy on resources, because if you're not sure of the frequency, you will probably set a frequency of like maybe after every 1 or 2 minutes, and at times this can take a toll on the target system, because it will be bombarded with unnecessary requests when it doesn't even have the data, and it can also cause a serious performance issue on the source system as well, where we are just calling the target system without any data. So this could be one of the drawback, and you have to take into consideration all the drawbacks and the benefits while choosing this pattern. So in the previous pattern, we saw that the source system was unnecessarily calling the target system even when there could be no data. So to overcome this limitation of the previous pattern, we have the subscribe notify pattern. So in this pattern, the source system calls the target system and informs the target system that there are particular set of messages that the source is interested in. Not all the messages, but a specified set of messages. So it subscribes to the target, and then the target sends an acknowledgement. Now another thing to notice is that the target should be able to call the source system as and when required. If the target system is not able to call the source system, this pattern cannot be established. Now, which condition could be possible where the target system cannot call the source system? For example, your source system sits behind a firewall and only outbound connections are possible from the source system. In that cases, target system won't be able to call the source system. So we make sure that the target system is able to call the source system. Only then the subscribe notify pattern can be established. Now once the source system subscribes to the target and the target sends an acknowledgement back to the source system, whenever after a particular period of time there is an event available which the source is interested in, the target system can establish a connection with the source and can send a stream of notification, not just a single notification, but it can send multiple notifications. And when the stream of notification ends, it can stop the message when the stop condition is received, and then the source can send an acknowledgement back. So this is how the subscribe and notify pattern works. So the benefit over here is that the source system is not unnecessarily communicating or polling the target system and causing stress on the resources, but it's the target system, whenever it wants, it notifies the source system and sends a stream of notifications. So a classic example for this would be when you implement a CI/CD pipeline. So there is a concept called as webhooks. So you go to your Git repository, it could be GitHub, GitLab, or any of this, and you paste your Jenkins server URL, right? And whenever there is a new commit to the repository makes sure that it calls the Jenkins URL. But the condition is that the Jenkins server should not be behind a firewall and any connections should be possible towards the Jenkins server. So this is one particular example where you can implement a subscribe notify pattern. Having a real-time or near real-time communication is not possible in every case. It happens when the target system needs to do heavy lifting while processing the message. So in such scenarios, if it is a request reply pattern via a RESTful service which usually gets timed out after maybe 5 minutes, the source system is left with an uncertainty whether the message has been successfully accepted and processing has been started, or whether the message was invalid and the request has not been received at all. So to address such concerns, we have the quick acknowledgement messaging pattern. So how does this quick acknowledgement pattern works is, we send a request to the target system, and to eliminate the uncertainty at the source, because the target system is going to take a long time to process the request, right? And we cannot wait for that long time because the request will obviously get timed out if it is an HTTP based connection. So the target system receives the request and instantly acknowledges the request, and maybe it will return you some unique identifier with which you can track down the request later on. So the source system is now certain that the request has been received and for sure it will be processed, or at least the source system will understand the status of what the request is. So after a period of delta t, that is the time difference after the acknowledgement and when the response is ready at the target, it can get back the response. Now to implement this part of this quick acknowledgement pattern, it again depends on other patterns. We can implement the request and acknowledgement pattern instantly, like you call the target system from the source, and in target you put an async scope and do all your processing in the async scope and instantly return a response back. But make sure you validate the request first, and then you start processing and send the response. So it processes in async scope and you instantly return the response. Now for the source system to be able to realize when the response get ready, it can again make use of other patterns like the polling mechanism. If the status is being updated to some database, so it can continuously poll the database to realize the status of that message. If the message is being pushed to some destination queue, it can continuously poll the destination queue, and based on the identifier that has been returned by the acknowledged request, it can compare the two identifier and check if the request has been completed and relate the response with that particular request. So the beauty of this pattern is that it in turn uses another patterns to fulfill itself. So here in case if you have some long running processes, use this pattern so that the source system is quickly gets an acknowledgement, and later on it can get a response. So the practical examples of this messaging pattern is like you order something from an online shopping website. So it doesn't happen, all the process doesn't happen quickly, right? But to ensure that your order is safe with them, your money is safe, and they have your order, what they do is they quickly acknowledge your order once the payment is successful, and then depending upon the multiple condition, availability of product, availability of manpower, you continuously get a response back from the target system. Let's take an example of a request reply pattern. The source system, that could be any user, sends a request to create a user in the target system. The target system receives the request, persists the data in the database, and returns an ID back. But when the ID was being transferred over the network, it failed to reach the source. It could be due to unreliable network, or maybe the source system lost the connection. So the source system thinks that the request did not get processed, and he retriggers the request. So what happens when he retriggers the request? There are chances that the target system can again create another user with a different user ID, but the details will be same. For example, if we are persisting ID, name, first name and last name, so we'll have two different records with different IDs, but the data will be same. So it's basically a data duplication happening, right? So to get rid of such problem, we need to establish an idempotent communication pattern. What does idempotency means? Idempotency means that once you send the request at the first time, the changes are made. But if you send the same request again and again, it will have no effect to the target system. For example, take the put request. If you send a put request with, like, you want to update the name, or you want to update the whole record, it gets updated. But after that, if you send the put request with the same detail, even though if it get updated, there won't be a visible effect, right? But in case of post, if you post a request and you post it twice, there are chances it will get duplicated because it doesn't have the ID. The ID is getting generated at the runtime. So that is what idempotency is, that it doesn't have any effect upon multiple triggers. So in such cases, what we can do is have a message filter at the target system. So what it can do, when the request is received, we have a message filter at target system that can basically use an object store which will have a track record of whatever the request is received, and it will compare the new request with the previous request. And if it finds that the request is duplicated, it will just send back the response of the ID that was generated for the request. It won't create, but instead send a success response, not even a bad response. It will send a success response, and it will mention that okay, this is the ID, maybe with ID 1, so it will send back the ID. So this is how you implement an idempotent communication. So basically in Mule you have a message filter and apply use an object store so that you store the record of that particular ID that was generated. So this is how we implement an idempotent communication. Now in some cases you might have consumers of your API who demand data in different formats. For example, we have an experience API which returns the details of products to different consumers, but some consumers want the data in JSON format, some might want in XML format. So in such scenarios, it's beneficial to use a content negotiation messaging pattern. So how do we implement this? The source can use the accept header and send the data type, that media type that it's interested, like here it's interested in application JSON. So depending upon the accept header, the target system will return a content type application JSON, and again based on accept type XML, it will return the XML type. So this is how we can implement a content negotiation pattern. So in Mule, this feature doesn't come out of the box. We might have to evaluate the header using the choice or data view transform and accordingly return the response. We have already seen this scatter gather in the beginning of this video. So we use this pattern when we have the same copy of messages which has to be sent across multiple targets which are independent of each other. So instead of using sequential processing, we can leverage scatter gather because the request gets scattered across multiple systems and they are independent of each other. And once they send the response back, the response is collected or aggregated, and the parent thread then again starts with the remaining process. So this is synchronous, just that the parent thread is blocked for the duration where the child threads, each of the child thread is successfully completing and sending the response, and it gets aggregated. So with this we end with the synchronous messaging pattern. Let's move on to the asynchronous messaging pattern. So in synchronous messaging pattern, it's always blocking until, even though it is parallel, it blocks. So to get rid of this blocking mechanism, we have asynchronous processing. So queuing is one of the asynchronous processing. It's as good as a fire and forget pattern with an added reliability. For example, we have the async scope, and if we put an HTTP request in that async scope and it fires any HTTP request to some other system, it's good, it's asynchronous, but we do not know what happens to the request. The request might reach, the request might not reach, or it might end up with some exception, right? So instead what we need to do is we need to have some reliability. So once we push a message to some persistent storage, a temporary persistence, which is queue. So message goes to the queue, and then the target system can pick up the message and process it reliably. So this is what we do in queuing, but we do not wait for any response. We just push the message and the processing is done at the source system. But what if the source wants back the response? This is when we use correlated queues. What happens here is the source sends a request to the target. The target takes in the request and makes sure that the request has a unique identifier. It could be a correlation ID in the header of the message, and the target also takes the message, processes it, and keeps a track of that ID. And once the message processing is complete, it sends back the response again with the correlation ID. So we have a correlation ID which is being kept track end to end, right? So the response will be sent and again it will have the same correlation ID. So once when the response is received by the source system, it will check the correlation ID and finally update the status. So what happens, this is asynchronous in a way that the parent thread just dropped off the request and went back to do some other task. It was not waiting for this response. Instead, there was, when the response came, it was picked up by another thread and it correlated both the IDs, and that is how it realized the status of that message. So that's the reason it is called as correlated queues. Both the queues are correlated with each other using a unique identifier. Next we have is the publish subscribe pattern. To understand this, let me take an example. Suppose you have two kids in your house, okay, and you have a subscription of a book or maybe a magazine, which the kids require the knowledge of that book or magazine to appear for the exam. Now if you get one subscription of the book, so both the kids will be fighting amongst each other to read the book first, right? And that is what is a competing consumer pattern, right? These kids can be imagined as a consumers and they are competing with each other. They'll be obviously fighting with each other to quickly get the book. And once the kid gets the book, obviously in practical scenarios, when kid 1 reads the book, the kid 2 can read the book later on. But in case of queues and we have competing consumer pattern implemented, the message can be just read once, right? And the other consumer won't be able to read the message, right? So in this case, the kid 1 read the message and the second one can't read the message, right? Again, so what will happen? The kid 1 will be able to answer the questions in exam and the kid 2 won't be able to answer the questions in exam, right? So how do we solve this problem? We basically buy 2 subscription of the magazine so that there is no fighting for the magazine, right? There's no competing consumer pattern. So in such cases, we go for a subscription. So when should we go for a competing consumer pattern? When you think that if either of the kid read the book and either of the kid has to give, means kid 1 or kid 2, anyone can give the exam. So then it makes sense, because if kid 1 reads the book, he gives the exam. Kid 2 doesn't need to give the exam. But if kid 2 reads the book, kid 2 can give the exam and kid 1 doesn't need to give. But if both have to appear for the exam and you have one book which can be read only once, then this doesn't make sense, right? So in such cases, we need a subscription of 2 books and you solve the problem. So based on the same philosophy, we have the publish subscribe pattern, where the source publishes the message to the topic and each of the target who does independent processing has its own processing. It's not that any one of them process, then the whole process is complete. No, all the system want to have their own processing. So in such cases, you buy each of the target their own subscription and the same copy of message will be sent across the system. And the example of this pattern, you know it obviously, it's a topic where same message copy is available with multiple target systems. So that's it for this video about messaging patterns. I hope you found this video useful. Thanks for watching.